Okay, we're going to do one more vector example. Let's have our friend the jackalope just go out for the day, and the jackalope is going to go some distance in, let's say, 45 degrees, and then we'll put this on a northeast axis. So I can't quite get my y-axis in the right place. So we'll just make this, even though the jackalope, it looks like the jackalope is going up in the air. I wanted to show the jackalope from the side. So east, north, this is really, really messy. And then let's say the jackalope decides to go, I don't know, say 2 miles, 45 degrees north of east, and then the jackalope comes back at an angle relative to that, goes back in that direction. Let's say that this angle is 15 degrees, and goes, I don't know, I guess I drew that about 2.5 miles. I don't know, those were just arbitrary vectors. Let's ask what the net displacement of the jackalope was. The net displacement, of course, goes from the head of the first tail to the second, the head of the first vector to the head of the first vector to the tail of the second vector. This is our resultant vector, or net distance. It doesn't have to be a resultant vector. It could be the net displacement, which I'm just going to call, because it's neither x nor y, I'll just call net displacement, delta d, or we could just call it d. Doesn't matter. Okay, that's our net displacement. So this is our first displacement vector. Delta d1 is 2 miles, 45 degrees north of east. Our second, that's delta d1. Our second displacement vector, delta d2, that's a vector. Delta d2 is 2.5 miles, 15 degrees. 15 degrees what? Well, that's not relative to our northeast axis. Okay, so we can't do that. So we have got to put that on an axis, right? We got to always put our vectors, each individual vector, in order to write its magnitude and direction or its components, we got to put it on an axis. This is messy, but you can read it. And again, that's my east and that's my north. Doesn't matter. We can always move a vector parallel to itself. So we know that we could move that vector down to the origin. So what is this angle? What is this angle? What angle do we make with the coordinate axis, right? The south coordinate axis. Well, you're going to have to do some geometry, right? If this is 45 degrees, then this is 45 degrees. So what if this whole thing is 90 degrees, and this is 45 degrees, and this is 15 degrees, 45 and 15 is 60, then what's left? 30 degrees, right? That's 30 degrees. So this is, I'll just write 30 degrees. It's west of south. West of south, right? The south is down, and we are going towards the west direction from south, right? Towards the west direction from south, because this is west. Okay, so those are our two vectors, and we're summing those two vectors so that delta d, the sum, is equal to delta d1 plus delta d2. Whoops, keep on making mistakes, little mistakes. I catch them. Delta d1 plus delta d2. So we want to sum those two vectors. In order to sum those two vectors, we want to take their vector components. So I'm going to take each vector. Let me just draw right on top of it. I'm going to take each vector. Let me make them purple. Let me draw it a little neater. Right there, that's the vector. And I'm going, well, it's a little messy. Okay, I've redrawn that a little neater, so hopefully you can read it. So now what I'm going to do is I'm going to drop the perpendicular down to the axis. There's the perpendicular, so that you can do the x component and the y component of delta d1. The x component goes to that perpendicular, and the y component, really, I mean, we could draw it on the y-axis, but whoops, the y component, whoops, come on, oops. Okay, let me try that again. I had a little trouble there. Draw the x component there and the y component there, right? So the x component plus the y component equals resultant. In this case, the resultant is just I'm just drawing the components of delta D1. So the components should add up to be delta D1. Okay, so this is delta D1 sub x, and this is delta D1 sub y. So those are our x and y components. I shouldn't have put a delta. It's just making too much writing, but that's okay. I started that way, so I'll continue. This angle, call it theta, theta 1. And we know that the length of delta D1, which is, we can draw either as an absolute value of the vector or just drop the vector sign. We know that's 2 miles. And we know the angle, theta 1, is 45 degrees. And so then we can do the geometry of the right triangle, and you find that the sine of theta 1 is equal to opposite, which is delta D1y, over hypotenuse, which is delta D1. And so therefore, we find that delta D1y, the y component of the delta D1 vector, is delta D1 sine theta 1, which is 2 miles times the sine, which equals 1.41 miles. Okay, that's the y component, 1.41 miles. The x component, we can do cosine theta equals the cosine of the angle is the adjacent delta D1x over the hypotenuse delta D1. So therefore, delta D1x is equal to, I'll just write it out, 2 miles times the cosine 45 degrees, which you might have recognized because cosine of 45 equals sine of 45, and that's just 1.41 miles. So each of those, I guess I didn't really need to do that, each of those is a length of 1.41 miles. So we found the components of delta D1. Excuse me. Let's go ahead and find the components of delta D2, the second vector, which isn't in this picture anymore. So let's go ahead and draw in the delta D2. What color do we want to make it? I guess I'll make it green just for the heck of it. Draw in delta D2. I didn't really give myself enough space, so I'm just going to draw it a little smaller, even though that is not to scale, not to scale, not to scale. We'll call this theta 2 because that's the angle that we have. It's 30 degrees west of south, right? That's theta 2. Theta 2 is 30 degrees west of south. So that's the angle that I drew in there. And then we drop our perpendiculars, and I'm just going to go ahead and draw the components because we know it's the right triangle that makes up that and that. Okay, there we go. So these are I'm drawing with a triangle. So this is delta D2y, and this is delta D2x. Okay. So just to make sure we understand that this is the vector, this is that vector, and I'm just trying to figure out its components. So you should not be writing in the corners like me, but let me go ahead and write in blue as if I'm writing on the next page. What we can find is that the sine of theta 2, look at the triangle, right? The opposite side over the hypotenuse, SOHCAHTOA, opposite side is delta D2x, and hypotenuse, I didn't draw it, the hypotenuse is delta D2 over delta D2, so therefore delta D2x is equal to delta D2 sine theta 2, which is 2.5 miles, sine of 30 degrees, which is 1.25 miles. If you don't know the sine of 30 degrees is a half, just plug it into your calculator. And then we do the same thing. So either we can use the two sides that we know, 1.25 miles and 2.5 miles, and the Pythagorean theorem to find the third side, we now want to find delta d2y, or we can just go ahead and say, oh, the cosine of theta 2 is equal to delta d2y, the adjacent side over the hypotenuse, delta d2. So therefore, delta d2y is equal to delta d2 times the cosine of theta 2. Sorry, this is so squished in, but I want to make it all fit on one page. And so we can go ahead and just plug in 2.5 miles times the cosine of 30 degrees, which is 2.17 miles. So we've got, whoa, what's going on? 2.17 miles on the y component, and the x component is, we said, 1.25 miles. Okay, so we've now broken our two vectors into components, and we know, and this is the key, right, is whoop, 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 whoop. We now need to sum them, so we need to add them together in order to find the resultant vector that the bunny with antlers went. Okay, so therefore, we can write delta D is equal to delta D1 plus delta D2. Therefore, we can break these two vectors on the right up into components. So we've got delta D1x in the x direction plus delta D1y in the y direction. That's delta D1 plus delta D2, delta D2x in the x direction plus delta D2y in the y direction. That's delta D2, delta D2, delta D1. And we know that we can add components in the same direction like scalars, so we can rewrite this as delta d1x plus delta d2x. And again, if you were on top of things, you could have done that right from the start. You know, you just add the x components, and then you add the y components. Delta d1y plus delta d2y. And the x components point in the x direction. The y components point in the y direction. Careful, right? They're not all pointing in the same direction. The x components point in one direction. The y components point in another direction. So this cannot add like scalars to that. Okay, so we'll just go ahead and plug in. So I just copied the numbers from the previous page, right? Delta d1x, delta d2x, delta d1y, delta d2y. Just copied it from the previous page. And so now we add those. We got 2.66 miles in the I direction, or in the x direction, plus 3.48. I hope I did that sum right. 3.48 miles in the j direction. This is the resultant displacement. Ta-da, ta-da, ta-da. There you go. Answer. I asked, what is the net displacement, or the resultant vector of the bunny with antlers, the jackalope? And there it is. He or she, I guess we don't know, they went 2.66 miles that way and 3.48 miles that way. Uh-oh, that is incorrect. So first of all, I drew that not to scale. Let me try that again. Draw that to scale. 2.66 miles that way, 3.48 miles that way would give me a resultant vector of that. That is not correct. The bunny, the jackalope, went that way. So what did I do wrong? What did I do wrong? What did I do wrong? I know what I did wrong. I'm asking you what I did wrong. Since I'm not getting any answers, let me go back to the other page and show you. So it's the signs, right? We didn't pay attention to signs. And this is where we really, really need to pay attention to signs. What color should I write in? Let me do light blue. So first of all, let's start with delta d1x. Nope. This is just going to get messy. I'm just going to use some highlighters here. Let me unhighlight some of these things. Nope, that's not going to work. Okay, so I'm just going to pause. I'm going to use a blue highlighter here. So let's start with delta d1x. Right there, what direction is it pointing in? Positive. So that should be a positive number. Then delta d2x. What direction is that pointing in? Compare it to the east axis. That's pointing in the negative direction. So I should have had a negative sign in front of that. You've got to pay attention to the negative signs. And then let's look at delta D1y. Positive direction, delta D2y. Negative direction, right? Delta D2y, negative direction. Let me undo all that highlighting and just again, just highlight the arrows. Positive direction, negative direction, negative direction. There you go. So the delta D2x and delta D2y should have been negatives. So let's come back here and say delta D2x should have been a negative and delta D2y should have been a negative right there and there. So what we end up getting is, we were wrong, 0 points. And what we end up getting is 1.41 minus 1.25, which is 0.16 miles in the I direction, plus 1.41 minus 2.17 minus 0.76 miles in the j direction. So now the resultant vector, that is the resultant vector, and that is indeed the correct resultant vector, resultant displacement. Let's just draw it, right? So we've got 0.16 miles in the x direction. Oh my goodness, I'm having troubles, you can't see, okay. And 0.76 miles in the minus j direction, because there's a minus sign there. 0.76 miles in the minus j direction. Again, draw it to scale. There you go, that's a little better. And so the resultant displacement is right there. And there's an arrow here, the arrow at the top that was not meant to be there, but I'm not going to erase it. Okay. And so now this is our resultant vector, delta D, and this form right here is component form, right? Component form. So if I ask what is the vector delta D, and I don't tell you what form I want it in, this is a correct final answer. Final answer right there. But I could also ask for the magnitude or the direction, or the magnitude and direction, magnitude direction form, right? So you got to give me magnitude and direction. The direction is any angle that describes the vector. So I'm just going to say, hey, let's find this angle right here, and we'll call that theta for the final vector. And delta D, we know that delta D is equal to, by the Pythagorean theorem, the square root of 0.76 squared plus 0.16 squared, because a squared plus b squared equals c squared. So c is equal to the square root of a squared plus b squared. And so the length of delta D is 0.78 miles, and the angle is the angle that I've chosen to represent here, which should be at the tail. You should always do the angle at the tail of the vector, not the head of the vector. The head doesn't make sense. It's got to be at the tail. It's what direction it's facing. It has to do with the tail of the vector, which way the tail goes, right? Which way the head goes from the tail. Okay, anyway, theta from the triangle I chose is the inverse tangent. Do it for yourself, right, to figure this out if you can't see it, but it's the inverse tangent of the opposite over the adjacent. So that is theta. 78 degrees. Okay, so that's 78 degrees. So this is 0.78 miles, and this is 78 degrees. Okay. Okay, are we done? No, we are not done. Because 78 degrees relative to what, right? 78 degrees relative to what? Last thing is we got to tell us, always got to give me what your angle is relative to, what axis. So we've got the east axis here and the south axis here. So it is, if this is east and this is south, and the angle is measured from east going south, so it's south of east. South of east. 78 degrees south of east. 78 degrees by itself is not enough. 78 degrees southeast is not enough. It's south of east. Done. Have a wonderful night.